Well, good morning and welcome to today's webcast, Do's and Don'ts of Pressure Design in Piping Codes. I'm Adrienne Bloom, Managing Editor of Hydrocarbon Processing and Gas Processing, and I will be your moderator today. In this webinar, we take multiple case scenarios to compare the mechanical design for wall thickness across the industry major piping codes, ASME B31.3, B31.4, and B31.8. In this way, we develop a stronger understanding of allowable stresses, installation environment, corrosion allowances, and where manufacturing tolerances affect the minimum wall thickness. Case studies are based on the same pressure, temperature, and nominal diameter, but consider conventional grade B SMLS versus ERW and materials to high-yield materials. Now, joining me today for the event is Stu Watson, Discipline Manager for John M. Campbell's PetroSkills Mechanical Engineering Network. And unfortunately, due to unforeseen circumstances, Josh Gilad will not be able to join us for the webcast today. So following the talk, we'll have a short question and answer session, and you can participate in the Q&A session at any time by asking questions during the presentation. Just type your question into the Ask a Question text area in the bottom corner of your screen, and then click the Submit button. You may enlarge the slide window at any time by clicking on the Enlarge Slide button, and that's located below the presentation window. The slides will advance automatically throughout the event. And if you experience any problems with the program, please press the F5 key on your keyboard or close your window and relaunch the presentation using another media player. You can also visit our webcast help guide by clicking on the Help button below the slide window. Now I'll hand things off to Stu so we can get started. Stu?
Thanks, Adrienne. So welcome, everybody. Thanks for tuning in here. It's great to have so many people involved with this. So this webinar came up, and the materials that I've prepared here were developed from experiences during training sessions where I continually get caught up with various questions, and I wanted to try to address some of the issues that come up and try and formalize them in a more public forum. And so we're going to be spending some time this morning talking about design issues of pressures and temperatures, understanding bases of allowable stresses, and also getting into some of the details around mill tolerance. And Adrienne mentioned in there how we try to utilize some case studies to try and illustrate some of these points. So that's going to be our goal. And of course, focusing on ASME B31.3, 4, and 8, we probably spend more time in here talking about B31.3, but we definitely reflect on the pipeline codes. So we have quite a lot of material here. Just the only other comment that I would make is that for those folks that are tying in that use SI units, I have to apologize because most of the units in the presentation are in FPS. I would have preferred to have both sets of units in here, but I've been focusing on just using FPS units in the presentation. Okay, so moving right along here. So one of the first things that we like to think about when we start talking about piping design is our basis. And from a mechanical engineer's perspective, most of this information gets handed to us from a process group. But I like to sort of start off by thinking about some of the factors that play into this and better understanding where the process design has come from, i.e., what is the design system pressure? What is that design temperature? And normally that's coming from what is the maximum operating condition of a system. We have our normal operating, we have our maximum operating, and maximum operating is going to be a function of maybe there's a high pressure switch on a pump that's going to shut down. And that's not our design pressure. That's our maximum operating point. And our design pressure has to be some margin above that. Usually that margin is a function of the relief system, making sure that we're not operating at the relief set point to avoid simmer and leakage and so forth. But often I find people miss that detail. And then I also ask about what are the off-spec operations? Is there a maintenance activity? Is there some process fluid surge pressure? are there future modifications and upgrades that we need to think about in the definition of the design pressure and temperature? And then the impact that this has to the mechanical engineer or the piping engineer when he starts thinking about not just the specification of equipment for vessels, and vessels, pumps and compressors, but also the smaller items. Valves and specialty piping items are key components which they're small, they're often overlooked, and I really wanted to just make sure that we don't lose context of all the details in the system. When we start talking about the piping design, then there is a lot of details such as the flange selection, class of material. I'm sure people have seen the flange selection tables, and we're going to be touching base on these here this morning. As well, we're also going to be jumping into the piping design and wall thickness selection, how the D rate for temperature occurs on materials with regarding to allowable stress. Having some cognizance to minimum design metal temperature is also a feature. As the design temperature falls, we need to be cognizant that materials have got limited minimum design metal temperatures. We're often thinking about what happens on the high side, what's the maximum temperature, but we need to realize that there are perhaps ambient conditions or maybe process conditions which are going to drive minimum design metal temperatures. In this webinar, we don't have quite enough time to jump into that, nor do we have the time to think about the thermal expansion and cyclic effects, expansive stresses, which the piping designer needs to be cognizant of. So one of the best ways to understand our basis of design is to look at a real example. So here we've taken crude oil from a tank, and we're pumping that over to a process unit. And normally that pump's running at 390 pounds, and we've got a pressure switch on that pump that's going to shut down that positive displacement pump when it reaches 500. So in this condition, we'd call the maximum operating pressure 500 pounds. So then the question would be, well, what is the system design pressure and temperature, and how should I set up my relief system in this process? Well, this is fairly straightforward. Generally, industry takes the rule of about 10% overpressure from MOP, and I would set my maximum design pressure at 550 pounds. There may be a bigger question about temperature, and we don't quite have enough information here to define the design temperature. But if I assumed an ambient condition, then I might start with a minimum design temperature of 150, or take my operating temperature and add 50 to it. The other way to look at this might be to say, well, based on the flange rating, an ASME class 300 flange, that rates out at 570 pounds at 600 F, so maybe 600 should be my design temperature. We're going to see that this gets a little more complicated in a second. So finally, what's my relief set point? Well, relief set point is always the weakest link in the system, in this case, the 550-pound design. And keeping these things organized in your mind as you go through is very important. We need structure here. So in this particular example, the pump, this system has a maintenance activity. And during this maintenance activity, they use low-pressure steam, which is superheated, and that superheated temperature is way above what the flange rating, the class 300 flange would be at the 550-pound design. So we have to look at this and go, well, do we need to upgrade now to a class 600 flange? That would be a question that we'd have to ask and work out the questions and so forth, the issues associated with that. But also, is there a limit that would limit the steam coming in? Is there some relief system that would limit that steam pressure coming in and therefore would be able to regulate to a lower design pressure and keep within that flange rating. So these are issues that we regularly get into with our process engineers, trying to better understand what is the design pressure and temperature. And I think most people can connect and realize how important having this clearly defined is. The system design pressure and temperature is going to affect not just the piping design, it's going to affect that pump, it's going to affect valves and valve seals. So having this information up front and defined clearly is very important for us as it moves forwards. So once we have a clear definition of pressure and temperature, the first thing I want to try to explain is in B31.3, the allowable stress and the behavior of allowable stress with temperature. And in this case here, I've grabbed a couple of pages out of table A1 from B31.3, and we're looking at two different sets of materials here. And the first material that we're looking at here is API 5L X60. And the reason I bring that up is because a lot of people don't realize that API materials are actually inside of the B31.3 code. The intriguing part of this is that when we look at the, you can see the yield strength on the X60 material at 60 KSI or 60,000 PSI. And you can see the allowable stress, which is flat at this point, 25 KSI from 100. It goes all the way up to 400 when you see it on the next page. But the reason that I bring this up is when we compare X60 material to A106 material, you can see that the A106 material is good for 20. Of course, the higher yield material does have some additional allowable stress there, but in B31.3 you have a very much limited ability to utilize that allowable stress, and that's because in B31.3 that's coming from a fraction of the ultimate tensile strength versus a fraction of the yield strength. So when I start to, if I was to apply this to an actual application, here we've taken a 12-inch pipe standard wall and run calculations out using the allowable stresses, and you can see how these different materials compare. This is all the same wall thickness, 375 wall, and the only difference between these materials is their allowable stress, or a fraction of their ultimate, and the joint efficiency on the different materials. And it's always a surprise how A106 grade B does quite well over such a wide range of temperatures. I have the whole chart here cut off at 700, and you can take A106 up higher temperatures than this, of course. The intriguing part is the API 5L materials stop short at 400 degrees Fahrenheit. That is as per the code. But the key that I really want to point out here is that piping materials tend, especially carbon steel materials, have a flat allowable stress from 100 up to 400. And if we're working with stainless steel materials, we'll see that that is up to 300 degrees before the stainless steel materials start to derate. And so having an appreciation of where the allowable stress is coming from and how that's impacting the design is really what I'm trying to communicate here. We're going to talk about the joint efficiency in slides coming up, but I just want you to be aware of some of these details about the source of allowable stress, where it's come from right here. So the next thing that I wanted to try to appreciate is that with all these different materials that we have on the market and the different design codes that we have, is how they relate to each other and why you might select one material over another. And here we see the ultimate stress for A106 and A53 grade B and API 5L X42. They all have an ultimate of around 60 before that ultimate starts to increase for those high yield materials like X60 and above. And then when I compare yield strengths, you can see A106 grade B materials, 35 KSI, and then the 5L X42, we actually get 42,000. We start to see that increase in yield stress in those API materials. Well, this is fundamental to the design codes because of the basis. And here we see the dotted red line is the allowable for B31.4. This is 72% of yield. That is the allowable stress in a liquid pipeline scenario. And here we see, or liquid or gas, and here we see the allowable stress for process piping. Obviously significantly lower. We try to bring the allowable stress down in process piping because of the proximity to other equipment and increased personnel safety, so the allowable stresses come down. Also, when you think about the utilization of pipelines versus process equipment, we can see far harsher infrastructure in refineries. There's a lot more expansive stress, and that cyclic behavior brings down the allowable stress. And that is, in part, the reason that we see lower allowables in B31.3 versus 31.4. I have an interesting example later on that really communicates the massive difference in safety factor between the codes and why we have high yield materials in pipelines rather than in facilities. So now I've taken another snapshot out of the code and we're looking at the joint efficiency, the E factor that I was talking about before. And I bring this up because of the variation in joint efficiency. And those that have worked with API 5L will be aware of the different kinds of joints. Perhaps what you don't realize is that if you look at API 5L within B31.3, it shows an array of different joint efficiencies, whereas in the other codes, such as B31.4 and 8, we see a lot less variation in that E factor. And I've got a good comparison coming up in just a second. If we look down below, you can see seamless pipe, ERW pipe coming out of the same code. So I think most people can understand where this is coming from, but really the benefit comes when you start comparing across the different codes. And so you can see here for A53 and A135 how B31.3 has a more aggressive stance on this joint efficiency. And that is going to make a substantial difference in the calculated pipe wall thickness. So understanding where the joint efficiency is coming from and that the joint efficiency is not flat, it's going to vary based not just only on the material specification, but also the design code that you're applying it for. So those two factors are very important when we start thinking about joint efficiency. And you can see at the bottom of the page here, I've picked out ASTM A671 type 12 and type 13. And the reason that I did that was because of the subtle difference in the type designation that can result in a substantial variation in the joint efficiency across all codes. And so there needs to be some sensitivity here, independent of your project, as to where is that being specified and carried through all the way from the engineering through procurement, supply, and installation. Is joint efficiency is a big factor that affects our design, and tracking subtle details such as the type number or grade or the type of weld joint that's on that pipe is an important part of the specification process. So talked about our piping design, moving onwards to our flange rating and flange design. And here you can see this is straight out of ASME B16.5. Now we're talking about ratings on flanges, and this is the table 2.1.1, where we're talking about A105 type material. And this would be typical flanges that you'd have in an A106 grade B piping system. And the reason that I show this is because understanding that this chart is looking up allowable stresses per class, and that allowable pressure on that flange is a function of temperature. And the reason that I want to focus on this is because if you remember our piping system, the piping allowable stress started to derate above 400. Here in our flange system, the flange starts to derate above 100. So many times I'm talking with people and they say, what's the MAWP on that flange? And they say, oh, it's class 300, it's good for 740. And the reality is that varies based on, well, what is the design temperature? And having some cognizance that this is a line that is curving downwards from 100 when you make that selection. Not just that, but also the grade of the flange. So here we see, you can see this also applies for castings A216 raw product grade B, WCB, and grabbed another table out of B16.5 right here, where you can see LCB A352. And at the same conditions, class 300 and 400 degrees, you can see that flange is only good for 615 pounds. So there is a lot of sensitivity to the material as well as the temperature here. When we start looking at stainless steel flanges, again, we see different allowable stresses on stainless steel flanges, and the difference between a low-carbon steel flange and a regular carbon steel flange, low-carbon stainless steel flange and a regular carbon content stainless steel flange makes a significant difference in these tables as well. So be aware that these tables exist when you're making specifications on your flange materials. So what we did here was take, again, we're back on the 12-inch pipe, and you can see the two lines there for class 300 and class 600 flanges, which are curving downwards from 100. And then I ran calculations for different pipe wall thicknesses in A106 grade B material. And it's not common that we look at charts like this when we're trying to make pipe wall thickness selections. Many companies have their own internalized piping specifications that make this process a non-issue. The pipe wall thickness is done for many engineers. But if you're trying to prove the basis of those piping specifications, then generating curves like these are quite helpful to understand where is the operating window or the operating envelope of that specification. So if I fixed a design temperature limit of 350 Fahrenheit here, and then my advance is not working, that's good. Just a second here, guys, as I get this back to where we started. This slide doesn't seem to be quite working quite properly. But if you can see, there is a limit here where 350 crosses the flange of a class 300 flange. And in that situation, at a little over 600 pounds, we would see that there is a box there that would limit between 600 pounds and 350 F, a design limit for a 300 flange. And that operating window or design window would be flange limited. If I increase that up to, and I'm not sure why that's not turning out in that animation. If I increase that to the 600 flange, then you can see that the pipe selection for extra strong becomes the limiting component and not the flange. And so this is a key component as we start to analyze pipe wall thicknesses and flange limits, which component is limiting the design. The intriguing part about this is that in this particular chart, I've used seamless material, and the E factor for seamless material is 1, of course. But if you were to change in your contract specification, when you go out to purchase the E factor from 1 to 0.85 for ERW, then this chart here is going to change significantly. Understanding that all of the factors that we've been talking about, not just the allowable stress, but also the joint manufacturing of the pipe, as well as the design code, is all issues that need to be considered. When I compare this to B31.4, B31.4 has an upper design limit on the code of 250 Fahrenheit. So you never reach the point in B31.4 where the allowable stress starts to derate. In B31.8, there is a derate factor where they start to derate above 100 degrees Fahrenheit. They start to derate from 100 to 450. But the pipeline codes are limited in their temperature of application, 450 being the maximum for B31.8. And so we don't see quite as much of this in the pipeline codes. But do realize that there is a temperature derating factor in here, and that flanges derate usually more quickly than pipe does from that 100 point. Okay, moving right along. There is always a number of purchasing and specification issues that come up during the sessions that I have, and one of the things that I frequently see is many of the pipe manufacturers sending out handy quick lookup tables to people, and I always bring up ASME B3610M, which is for carbon steel piping, and there is a separate specification for stainless steel piping. But this outlines the original source material for dimensions that fabricators should be building their pipe to. And I've just, of course, again, 12-inch pipe, taken the section out of that code. And really, I just want to point out that there is a significant difference here between Schedule 40 and standard wall, and Schedule 80 and extra strong. They're not the same thing, and I've seen many a mistake occur from assuming that they are the same thing. So please make sure that when you're running through your specs, you call out exactly what you intend to. I have seen client specifications where the wall thickness itself, the 0.375, is called out on the piping spec to avoid any confusion. So make sure this follows through, not just your purchase orders. I also like to see that kind of information on isometrics going out to the field as well. So some of the assumptions and issues that come up in this area where we see differences between schedule and what is Schedule 40 and what is standard wall. They're not always the same thing. There is also misunderstandings regarding temperature derate between piping and flanges. And then also some of the issues that I brought up there regarding joint efficiency for specific grades. And I mentioned at the bottom of it, you can see at the bottom of the that last point there, 304L versus 304/304L. Today's world of materials, we frequently get into the specification of or get supplied with dual specification materials. We like to use 304L when we're trying to weld piping and flanges together because of the sensitization issues of chromium in stainless steels. And so we request 304L, but are supplied 304/304L. Well, that's not a problem. If we're requesting 304L, because the design pressure of 304L will be lower than what that 304/304L flange is capable of. We have to be, I bring this up because I've had situations where people are utilizing the benefits of a dual specification unit. And if we're going to go down that path, then we need to be cognizant that now I'm not ordering 304L anymore. I'm ordering a dual spec material which has to be compliant with the strength requirements of 304 and the low carbon requirements of 304L. And if you look at the flange tables in B16.5, you'll see the substantial difference that exists between the design pressures of those two flanges. All right, so here we are. We're going to have a few minutes talking about mill tolerance, which is always a favorite subject. And mill tolerance is a fabrication tolerance on pipe. It is not specified, as in how much mill tolerance is not specified within B31.3. That's going to be something that comes from who's manufacturing it. Perhaps it's on the supply purchase order. Sometimes you can negotiate a smaller mill tolerance. The actual piping specifications will also give indication as to how much mill tolerance that pipe will have. We frequently hear 12.5%, and that is a function of A106 grade B. That is how they make that pipe, and that is where that's coming from. The trick in the application here is how is this applied to the different design codes. And I'll start off with B31.3, and you can see I've grabbed right out of B31.3 the statement there, and the last line inside the box there where they say minimum thickness T for the pipe selected considering manufacturer's minus tolerance is not less than TM. So here the mill tolerance is an additional component or additional allowance that we need to be cognizant of in the design and specification of pipe. And that is a very different statement than what is in B31.4 and B31.8. The T in this calculation here is the thickness or pressure that you can see on the right-hand side, and the C is the sum of allowances for erosion, corrosion, or if you've got mechanical allowances such as threads or grooves where you would delete material for that. And so understanding that this is the thickness or pressure based on hoop stress, this is commonly used when we start doing our first pass for wall thickness selection. And just moving on from here, the nice thing about B31.3, and I'm not sure how many people realize this, is that towards the back of the code, there are a wide number of examples. And this makes me think back to the days when I was at university. I'm trying to work out how something, how to actually do something in my classes, utilizing those appendices that are in the back of the code there, and do have a read of the various design examples that are back there, because a lot of good answers come out of that. In this particular case, they use 12.5% mill tolerance. That's pretty typical for a A106 grade B material. API5L is generally 10%, and again, as I mentioned, you may have special orders there with lower mill tolerances. And they work through this example in Appendix S, and they show you how it is an additional allowance which is added to that code. I'm not going to walk you through that code. I figure that you guys can grab B31.3, look at that appendix, and walk through that. In the interest of saving time, I'm going to keep moving here. So what I want to talk about is the reflection to the pipeline codes, 31.4 and 8. And here there are clear statements. You can see I've grabbed extracts from B31.4 and 8 here, and I've tried to add the locations of where I'm pulling those extracts from the codes. That within the design factor F, so in B31.4, that is that 72% of SMYS, or 72% of yield, there has been an allowance made for mill tolerance. In B31.8, where that F factor varies based on location class, again, that is attributed to being considerate of under-thickness tolerance, is what they call it here, from manufacturing. And so the pipeline codes say this is wrapped up within that F factor. So do understand the significant difference between those two codes. What the pipeline codes go on to talk about, though, is the fact that there is a plus or minus wall thickness, then there is a certain out of round, and that out of round may lead to an increased onset of collapse because of the nature of external overpressure collapse, that out of round should be considered in those calculations. And you can see the statement there straight out of B31.8 talking about considering this aspect. The last line item that I have at the bottom of the page there is the Appendix F mandatory design section for header design. They take you through compression headers, how to go through and design headers. And within that appendix, again, just like we talked about on the previous page, the mil tolerance is assumed to be part of the F design factor. And so it's effectively excluded from any part of the calculations. It makes life a little simpler for us. So if I just flip back to B31.3, the next thing I want to do is just clarify the code and the process by which we apply mil tolerance within the code. So the first part here, well, I've got a graphic coming up that helps explain this. So the first part here is obviously making a calculation for pressure, and we start off with that calculation that I showed you on the screen earlier, basing our wall thickness on hoop stress and working out what other factors such as corrosion or mechanical allowances, we have to add those in. With that information, we can make a slightly advised wall thickness selection, meaning going out, finding out what is the actual nominal wall thickness based on ASME B3610M. And then from that, we will actually deduct the 12.5% mil tolerance that would be necessary to make the correct calculation for B31.3. The final step 4 is a comparison where you can see the calculation at the bottom of the page there in red, where we look at thickness for pressure and allowances. It needs to be less than my nominal minus the mil tolerance. I'll explain why I'm being quite specific about this in just a second here. So here's my thickness for pressure. That's my calculation based on hoop stress. Then I've got some allowances here, corrosion, erosion, mechanical allowances if I've got threads, and that results with a calculated minimum wall thickness. So then I would make a selection of wall thickness from B3610M as to what is commonly available on the market. And with that information, I could then go, okay, now I've got a 12.5% mil tolerance that I'm going to take off that. Is that mil tolerance going to reduce my thickness to a point where I am still above my calculated minimum, or does it take me to a lower thickness where I start cutting into either my corrosion erosion allowance or into my thickness for pressure? So I like to appreciate what this looks like graphically like this because it makes it very clear as to where this is coming from. The next chart that I have here is where I've just run some code calculations. And this was actually just last week on a training session in Korea. And we ran, the section in blue here is B31.3 calculations, and the section in red is B31.4 calculations, liquid pipelines. So you can see my first columns here, A106 grade B and A53 grade B, and then the lighter blue color is API 5LX80. So you can see the 80,000 pound yield stress on that material as compared to the 35,000 pound for grade B materials. And then the variation in joint efficiency that occurs across the board on all those different materials, just looking at the blue section at this point in time. So I follow through and I make a calculation for TP, my thickness for pressure. I add in my corrosion allowance. I get a total of TP plus allowances of 0.38. And then from there, I would go and make an assumption. I'm going to go look up and select a wall thickness. So that first column there, you can see I've selected 0.438 for A106 grade B seamless. And from that, I'll make a deduct for the 12.5% mil tolerance. So my mil tolerance here is 0.055. So the second box that you see at the bottom of the page is something that I've seen occur in many occasions, where they take the TP plus allowances and then divide that or multiply that out by the mil tolerance. And the feature here is that you will end up with a mil tolerance that is actually less than the real mil tolerance. So they end up with a 0.048. The code is quite specific about this issue. The code brings up that the mil tolerance is really a function of the nominal thickness, not the other way around. And I always bring this up. I've seen people get into situations where they end up with an under-thickness situation. The reason that I show X80 material here is because X80 is not used in process facilities, and I like to demonstrate why that is. So in this situation here, I would need 0.438 wall thickness for A106 grade B, whereas for X80, I would need 0.330. It's not a substantial, it is a reduction in wall thickness, of course, but it's not a huge reduction. And that is, again, because our allowable stress here for B31.3 is based on a fraction of the ultimate tensile strength versus a fraction of the yield strength. When you compare what X80 is capable of in B31.4, take a look over in the red section. Of course, the joint efficiency goes from 0.95 to 1, and we also see the mil tolerance, the whole calculation about mil tolerance just goes away. And you can see that with API 5LX80, I can do that in 0.188 wall, very thin wall thickness. And based on the challenges that you may encounter in trying to weld X80 material, and the fact that 0.188 is so thin, often companies will have minimum wall thicknesses just from a general fabrication perspective, mechanical strength issues. Often we say a 0.250 minimum wall thickness, in which case X42 does that quite nicely. So I like to sort of see the different materials compared side by side like this, as it helps to explain why we select certain materials, and also that whole process about mil tolerance and how that works. So at this point, what I'd like to do is just surmise a few of the key points from the webinar here this morning. First of all, of course, when we're talking about design, pressures and temperatures, make no assumptions. Make sure that we understand where they're coming from and what they apply to. Realize that those design conditions, they're going to apply not just to vessels and piping and flange ratings, but also, don't forget, your smaller items. Specialty piping items are always an issue. Moving right along, we see also understanding that the design codes and the basis of the allowable stresses for those design codes varies. We saw that B31.4 and 8 is a function of SMYS, and B31.3 is a function of UTS. And that is a function of what do we do in process piping. We've got refineries, we've got a wide variation in process temperatures, a lot of expansive stresses. In B31.4, we've got pipeline design, we've got more static environments. Often the design strength on pipelines is a function of the installation stress, especially when we talk about subsea pipelines. The actual design and the limit on the pipe wall thickness may not be hoop stress, it may be a function of other stresses such as installation or longitudinal stress. Realize that the joint efficiency varies significantly by not just the material specification, is it seamless, is it ERW, but also the design code. Is it B31.3, is it B31.4? They are all factors that come in. Also your flange ratings, whether you've got a API flange or you've got an ASME B16.5 flange, those flange ratings vary according to the material and the class, but temperature is also a factor in here. So when we start talking about specification of materials, just be cognizant of specifically those issues surrounding stainless steel flanges. There's a big difference to carbon steel flanges, and the actual grade on flanges, on valves, is also a factor. Obviously, we saw there's quite a few steps here that we went through in evaluating a wall thickness and determining that for a project. I would just reinforce once more, exhibit the care and sensitivity to these specifications, not just in the design role where we are perhaps more sensitive to them, but also throughout all the other parts of your company and project. Not everybody has the same sensitivity to these details, and it's very easy, to lose context of a specific grade or material specification. That's why I try to highlight through some of the examples some of those issues. And last but not least here, talking about mill tolerance and how mill tolerance for B31.3 is a deduct from the nominal wall thickness, whereas for B31.4 and 8, that calculation for a design factor includes or attributes a portion of that design factor for mill tolerance. So just be cognizant that the two codes, or the three codes there, look at that mill tolerance quite differently. And just think about that as you're going through these calculations in the future. So it's at this point here that I'd like to move over to some questions and try and pick up a few question and answers. I do like to first of all say thanks so much for your time today and tuning into us. This is the course that I've mentioned earlier today and the course topics from that course. And you can see our URL at the bottom of the page there as to where you can get more information about that. But at this point, I'll just reach out to Adrienne as to what questions have come in that we may be able to help clarify.
Okay, thank you, Stu. That was a great presentation. And now we can have a few minutes to move along to some audience questions. We have about 12 minutes for that. So one good question we have that came in is, if I specify the pipe in the PO without mill tolerances, should I still consider it in the equation?
If I specify the pipe in the PO, should I still...
without mill tolerances.
I'm sorry. Can you go through that?
I'll repeat it. If I specify the pipe in the PO without mill tolerances, should I still consider it in the equation?
Yes, of course. Yeah. So the specification in the purchase order will list out for example, if you've got A186 grade B material that has a known manufacturing tolerance, the manufacturing process according to A186 grade B will define that manufacturing tolerance, and therefore that manufacturing tolerance should be brought into the equation. And this is strictly for B31.3. If you've got a B31.4 or a B31.8 design, then obviously it's not a factor. But yeah, you always need to think about that. And typically speaking, we utilize a 12.5% mill tolerance on carbon steel piping, unless it's API 5L, where we jump to a 10% mill tolerance. And that manufacturing tolerance tends to vary. I'm jumping off the top of my head now, but I seem to remember at 20-inch, that manufacturing tolerance changes from 12.5% down to 10%. So just be cognizant that they vary. They vary based on manufacturing method as well as the actual nominal size. Great question.
Okay, great. Thank you, Stu. Another question that we have that came in is, can you advise work that's been done in the area of natural frequency vibration and design steps to assure that the system is protected to avoid this area?
Can I have you repeat that just one more time for me, Adrienne?
Sure. Can you advise work that's been done in the area of natural frequency vibration and the design steps that can assure the system is protected to avoid this problem?
Context is everything, and understanding if it's a process facility or if it's a pipeline is going to be a big factor that needs to be first addressed. There is sections within both of the codes where they identify that resonance within a piping system is a factor that needs to be considered. The code does not specify by which the means that needs to be addressed, just that it needs to be addressed. I'm thinking about applications or examples for you, and the Alaska pipeline had massive resonance issues that they had to address, that pipeline being above grade or wind, and essentially a vibration issue. We see also similar things when we have spanning in subsea pipelines. In an onshore situation, we get into resonance inside piping systems, especially around compressors. And usually we will go off and do third-party analyses to make sure that the excitation frequency of the compressor is not driving the natural frequency of the piping. Not entirely sure that I've hit your question right on the head. A little more information, maybe we can get a follow-up email or something if you want to take this one to some further offline discussion. I may be able to try and find some technical papers and so forth and respond if you can help me out there with some more detail.
Okay, thanks, Stu, and we can certainly respond to questions offline later. I'll move on to another question for you. This question regards to slide 9. And in that slide, the audience member asks, do you mean that B31.3 is more conservative than B31.4 and 31.8? And if E is less than 1, the thickness increases in piping. Is this correct?
That's exactly correct. That's exactly what I'm communicating, is that the joint efficiency, which is going to affect all three calculations, is read differently from the different codes. And you can see that if you use A53 grade B ERW, B31.3 sees a 0.85 joint efficiency, whereas B31.4 and 8 see a 1.0 joint efficiency. And so the wall thickness, and that is part of the reason that if you go to, if I just jump down to my calculation example that I did towards the end, let me push that out, hang on a sec. This slide right here, you can see that in B31.3, we had to use 0.5 wall thickness pipe versus 0.38 for seamless. So you can see the first two columns there is seamless and ERW, and for B31.3, that's affecting wall thickness. The examples that I used over on B30 on the other side, you can see the difference in joint efficiency, and that is because X80, we talk about DSAW or ERW, they are both that's a 0.95 and a 0.85 joint efficiency, and that also affects the calculated wall thickness. So yes.
Okay, great. Thanks, Stu. Next question we have for you is, where the installation temperature, so say about minus 40 degrees Fahrenheit, versus the operating temperature shows itself in the thickness calculations. So where does that occur?
So installation stress is a big issue that we need to think about, and when I have to be cognizant when I talk about installation stress and maybe clarify what I'm thinking about when I talk about that is here is perhaps a offshore pipeline. When I'm lowering a pipeline to the sea floor, I have to put a lot of tension in that pipeline and therefore stress on the pipe. The bending stress and tension stress on an offshore pipeline installation is commonly higher than the actual operating stress. And that's what I mean by installation stress. When I'm doing plant fabrication at cold temperatures, I will need to be cognizant of the construction temperature, because a similar situation occurs from, we call it expansive stress, meaning we construct at a cold temperature and then we've got to actually operate at a higher temperature. In B31.3, well, actually all the codes say that you have to do some kind of analysis if expansion stress is excessive. It doesn't say when. B31.3 gives you some guidelines in terms of a flexibility analysis because you evaluate the change in temperature results in a certain amount of strain. But in B31.3, we assume that means go off and do a formal piping stress analysis using something like Caesar or so forth. The trick is working out when do you need to do that and when do you not need to do that. Often, many companies have internal guidelines that will drive you towards this is when you need to do a stress analysis, this is not. If my design temperature for a piece of pipe is 120 degrees Fahrenheit, normal operating, and my construction is minus 40, unless I'm tied up against a major piece of process equipment or up against a piece of rotating equipment, there tends to be a lot of, we have to bear in mind there is hoop stress and longitudinal stresses, and those longitudinal stresses, there is a lot of headroom for allowing that thermal variation from construction. There is no short answer to this question. To answer it completely, we would have to go back to B31.3, go do a formal analysis, and work out, is that too cold? So in a major project, we would look at the construction temperature and run a few sensitivity studies, run some basic Caesar runs to work out, well, is this going to be acceptable at this size or this size? And try and work out where we need to draw a line, and then from those case studies, go off and analyze the systems which we see are either high forces or high stresses resulting from the stress analysis. It's a great question. I'm sorry that if that seems vague, it's because the answer is complex.
Okay, thank you, Stu. And we have time for one or two more questions. Here's one that just came in. When is SS304L actually chosen over SS304? Is it mainly for temperature or process material specification requirements?
304L is usually a requirement for welding on stainless steel. When they manufacture stainless steel piping, and this steps into metallurgy, which is perhaps not my strong point and probably a subject for another webinar entirely, but generally speaking, if you're welding stainless steel pipe together, then when you weld the carbon on a regular carbon content stainless steel, the carbon will react with the chromium in a process called sensitization and reduce the corrosion resistance of that stainless steel piping. So because we usually have a care for how corrosion resistant stainless steel pipe is, that's why we're buying all that chrome in that stainless steel pipe, we spec a low carbon 304L, which is below 0.03% versus below 0.08% carbon, and as a result, the strength of that flange will drop. In today's manufacturing technologies, the advances in metallurgy and making steel, we have been able to come up with a dual spec product, 304/304L, meaning it meets the strength requirements of 304 flanges, and it meets the corrosion resistance after welding of 304L flanges. And we just have to be cognizant that if we are utilizing the strength of that dual spec material, we need to spec it as a dual spec material and realize that it is not a either-or situation. Great question.
Okay, thank you, Stu. Well, that is about all the time we have for questions today. We want to thank everyone for tuning in, and we want to let you guys know that the full recording, including what some of you with the audio issues during the beginning of the presentation didn't hear, that will be available for viewing later today or tomorrow morning. So the full recording will be up for you to listen to, again, if you'd like.
Right.
And thank you, Stu, and thank you to the audience, and that concludes the webcast. Thank you.
Yeah.